Hey, John here. First, I'd like to thank my Patreons that stick with me. Your support helps, even every little bit helps cover the cost of shipping and other such things that you end up having to pay for to get the parts I need to do these videos. So, thank you very much, especially to the VIPs, Bob and Tim. I really appreciate it. So today I want to talk about interrupts. Interrupts on the CPU, specifically the signals on pin 17 and pin 16. The signal on pin 17 here is called non-maskable interrupt. Signal on pin 16 is just plain interrupt. The difference between these two, as the name suggests, non-maskable, where the word maskable means to provide the ability to ignore or defer the recognition and handling of signals that might appear on pin 16. Okay, that is not a feature of those signals that arrive on pin 17. These are non-maskable. They're not deferrable. They're not something that we can disable in the CPU. These are absolutely going to be recognized immediately. And we'll talk a little bit more about what they really are by way of an analogy in a minute, but that's the difference between these two pins, okay? But otherwise, they're very, very, very similar, okay? The non-maskable interrupt and the interrupt signal are both pulled high right here on resistor network number 1. Okay, that's the only place you see the non-maskable interrupt connected on the retro board. I don't use it for anything. Okay, if you were to use such a signal like that, where you find it used is things like if your power supply is shut off and you know that the hold-up capacitors, the big filter capacitors, will discharge, in 400 milliseconds or something like that, you might assert the non-maskable interrupt, which the Z80 then would recognize as the power's about to shut off. Just abandon anything you're doing right now because the power is going to go off anyway, and make very sure that if you are in the middle of doing something like writing data to a disk or an SD card or something like that, you need to wrap it up or shut it down immediately. Certainly don't start anything new that could result in the corruption of the data on that media. That's the kind of thing you do with this, all right? And we don't have that signal on the retro board, so we don't use it for anything. That doesn't mean you can't do something with it, because it does get pinned out over here on this expansion header over here. It's right over here on pin 17 and 16 of the header, the same pin numbers that you see on the Z80. Okay, now interrupts are what we really want to talk about today. So I'm not going to say a lot more about non-maskable interrupts, other than to throw in a side comment when we get to the point where the discussion of interrupts diverges from what would happen normally on pin 17 here. Okay, so these two signals go into our Z80 CPU as is suggested, and they are used to stop the processing of something. Like, for example, by analogy, an interrupt signal would be something like on your phone. If your phone rings, you got one kind of a tone for a phone call, somebody wants to talk to you, you can either pick up the phone and handle it right now, or you can ignore it, or you can do something like this where you grab your phone settings and you can completely disable your phone from being able to alert you at all. When you do that sort of thing, that's what masking an interrupt is. Okay, now obviously you cannot do that to the signals on pin 17, like I said before, but you can on pin 16, and that's the difference between these two. Now I take the interrupt signal to the CPU, and it's connected over to the CTC. You can see right here, and these pins right over here. The interrupt is connected to the interrupt pin from the CTC, and it's also connected over here on the SIO, and these pins over here, same way. All right, so what does this really boil down to? That means that the SIO or the CTC, at any time they want, which I enable and disable through software control, we'll look at that in a minute, can ask the Z80 to stop what it's doing and service the attention that's required because something asserted a signal on the interrupt pin here. Okay? So to summarize, we have non-maskable and we have maskable interrupts. Non-maskable, the CPU will react as soon as the current instruction is completed. Okay? I mean, it doesn't literally stop right in the middle of adding two registers together. It finishes whatever it's doing right now, and before it starts the next instruction that it would normally process, it will service this interrupt. Okay? We'll talk about how that works in a second, but that's what this one means. The maskable interrupts are the same kind of a situation. However, the CPU will only react after they have been enabled. In other words, they're not masked to be shut off, and after the current instruction has completed. Okay? These are the ones that we're going to be dealing with. Now let's go back to one of our favorite user manuals here. I'll link to this below in the video description if you need your own copy, okay? In this manual, we have all kinds of things, one of which is a timing diagram that talks about what happens when an interrupt arrives. Here we go. There's a little narrative there, and then this picture right here. Okay, so this one here is the regular interrupt request. In other words, this is the maskable interrupt. Down here is the non-maskable interrupt. Okay, so let's start with the regular maskable one. This is where we're going to focus on today. All right. Now, we've already talked about how the Z80 controls everything, right? There's a machine cycle number 1, followed by optional machine cycles number 2 and 3, and so on to execute any given instruction. Machine cycle 1 is normally the time in which the program counter is sent out of the address bus. M1 goes active low, and the CPU reads from the memory the opcode for the instruction that's to be executed. Okay? Now, that's not how that works if there's an interrupt that has been asserted. Well, let's look here at the very last two, what they call T states, the two clock cycles. This is the phi clock that I've been calling that lately, that controls the Z80 and the system as a whole. All right? So on the very last clock cycle, on the raising edge, while it executes any instruction, the very last one, right, the Z80 will look to see if the interrupt signal is low. If it is low, and the interrupts have not been masked off, it will respond by performing a different version of the M1 machine cycle, right? M1 goes active, but memory request does not go active here. Neither does the read signal. So it's not going to read from memory. Yeah, it'll go ahead and send out the program counter because it's going to do that anyway. This doesn't get used for anything. What is special is I/O request will go low during the M1 cycle. During that period of time, is a special case that any peripheral that understands how the Z80, bus control works, can send data on the data bus here. That'll be read in by the CPU, and this data can be used to figure out what device generated that interrupt signal. Okay? After this point in time, the Z80 resumes the execution of what it normally does. Now let's take a quick peek at the maskable version. Okay? This is a little bit different. This diagram is also broken. There should be a line that goes down here and back up. This is the same situation that happens in the last cycle of some instruction being executed, but this time we're looking at the non-maskable interrupt signal that cannot be disabled or blocked, right? If it is low during the rising edge of the last M cycle of some instruction, the next machine cycle starts like this. You'll notice this is a regular M1 cycle. So how is this supposed to work? Well, there's one and only one thing that the Z80 can do in response to a non-maskable interrupt, and that is to directly call a subroutine at a specific well-known address in the memory. And this M1 cycle is the fetching of the opcode of the first instruction of that, what we call an interrupt handler. So the difference is NMI, there's no way to shut it off. There's no way to configure it. It's welded in. When it is asserted on the last rising edge of any instruction, you have a immediate call to a well-known subroutine in order for the Z80 to respond to it. And a maskable interrupt, it may or may not respond, depending on whether it's masked off or not. If it is on and it is seen to be active during the last rising edge, the peripheral device can supply some data down here that the Z80 can use to determine what it wants to do in response to the receipt of that signal. All right, so let's talk about our options, right? What does the Z80 do if it wants to process a regular interrupt signal? What does it do with that 1 byte value that it fetches during the interrupt, what we call the interrupt acknowledgement cycle, that M1? Well, it depends what mode we put the Z80 into. Quick history lesson. The people that founded Zilog, that manufacture the Z80, used to work for Intel, and they all worked on the 8080 CPU when they were at Intel. After that, they left in the mid-70s to form their new company called Zilog, and they decided to create a new CPU that is a superset of the 8080. And they wanted to be software compatible, but they also wanted to have more advanced features. So what they did is they decided that they would create more advanced features for their interrupt handlers to have fancier things, but they'd also have a mode of operation that is compatible with how the 8080 works. That way the software can work as is pretty much. You just take the firmware from an 8080, you build a new product, you don't want to use the 8080 anymore, you move on to the Z80, which is a lot easier to work with, right? I mean, it runs on 5 volts only. It has you can get them to run on faster clock speeds, and the clock signal itself is less complex. I'll let you Google that to get the details if you want. This is all well known. Nobody would use the 8080. That's why Intel themselves came out with the 8085 and so on. Well, anyway, some engineers left, created the Z80. That's why we have these modes, right? Mode 0 is 8080 compatibility mode. And the way this works is that during that M1 cycle, it reads that magical byte that we just looked at, and it takes it and it simply executes that as it would any other instruction. That's all there is to it. It turns out that some instructions are better than others to use. Okay, there's a special set of instructions called the reset instructions. There are 8 of them. And the way these things work is they represent a single byte instruction, which is critical. If the device is only going to be able to send 1 byte, the last thing you want to do is send the opcode of a 3-byte instruction. I don't even know what the Z80 would do. Most likely not what you'd want, right? There's some 1-byte instructions that are specifically designed to be used in this context, okay? They're called the reset, or restart, I should say, instructions. There's 8 of them, and what they are is a 1-byte instruction that calls a subroutine at a well-known address. And you can say restart 0, for example, or restart 8, restart 10 in hex 10, right? Those are the target addresses of the subroutines that you can call with the restart instruction, okay? Now, if the device is smart enough to assert an interrupt and then recognize what's going on the bus, in order to send this byte at the right time, it can control, in other words, tell the Z80 which one of these 8 subroutines needs to be executed. So if you have 8 peripherals, each of which can generate an interrupt, and one of them does, and it recognizes that the Z80 has entered an interrupt acknowledgement state during the M1 cycle, it can send one of 8 restart instructions so that the Z80, this is how the Z80 can figure out which peripheral device generated that interrupt, okay? So this is one way to do it. Pretty simple, straightforward. If you have a peripheral device that's not that smart, because you think about it, you're gonna have to recognize those signals, and if you're gonna build them with discrete logic, and you gotta remember this thing came out in like 1976. There's a lot of TTL chips you'd have to put into a circuit if you built something from scratch with discrete parts in order to decode that whole M1 cycle in order to send that back. So what Zilog did is they said, look, let's create a mode 1 that says, we'll let the Z80 do its dance, But if it's in mode 1, it'll just simply call a subroutine at address 38. That way I don't have to pay more money to make fancy peripheral devices that can generate these reset instruction bytes during the acknowledgement cycle, right? Saves you money, okay? Simple circuits where you only have maybe one device, or even if you have 2 or 3 devices, you can use this style. If there's more than one device, what would happen is you'd have to write a subroutine at address 38 that would go over and try and figure out what happened and why it's there. If there's more than one cause, it'd have to pull all the devices to figure out which one was responsible for generating the interrupt, okay? But this is a money saver thing. I mean, it is a kind of thing you do back in the day to save your customers money, to get more design wins. Then they decided this is too simplistic. If you do have a complex situation, what if you have more than 8 devices, okay? Or you just need a more sophisticated way of handling your interrupts. Here comes mode 2, and this is the mode we're going to be working with. The way this thing works is you fetch the 8-bit value during the interrupt acknowledge cycle that we just looked at. And then rather than executing that 1-byte value that it fetched during the acknowledgement, it's going to take that 1-byte value and it's going to use it as an index into a table. Okay, we call this a vector table. Because it's a table of pointers that all point to some subroutine, okay? And then call the one, I should say, based on this index number. And as we'll see, we can create a table that has up to 128 pointers in it. Therefore, the Z80 could have 128 unique interrupt handler functions for all sites of devices, okay? Now we're going to use this mode because the Z80 peripherals, the CTC and the SIO, as well as others, are specifically designed to pair with the Z80 and operate in mode 2. In other words, they do all the fancy schmancy stuff necessary to make all this work, okay? This is what we're going to look at. This is what we're going to do here. Now, before we dive into the code, let's have a look-see at our vector table here, okay? Now, this is only used for mode 2 interrupts, all right? So how does this thing work? Well, first of all, there's a thing called the I register inside the Z80 CPU. What it is it's an 8-bit value that represents the most significant byte. Remember that addresses in a Z80 have 16 bits. So there's the most significant and the least significant byte of the 2 bytes that comprise an address. So this is a 1-byte value that is the left half, the most significant half of the vector table address. Okay, so if your I register has the value FE, here's my sample I register here, then what happens is the FE value represents this left half of the 16-bit value where this table's contents are stored in memory, okay? There's an address, there's a value in memory. The Z80 thinks of the data in this vector table as a set of 16-bit values here, okay? Each one representing the address of some subroutine. All right, so let's see how this thing works here. If the I register is set to FE, the table will begin at FE00. Okay, this is the definition of what this thing does and what it means. At this address in memory, we have a bunch of bytes. We need to fill these in with 16-bit values that are the addresses of all these subroutines that we want to use as interrupt handlers. Okay. Now, the way each one of these handlers is then called, we have to enable the interrupts on the Z80. We, of course, have to set the mode to 2 in order for this to work. And when an interrupt is generated, the peripheral device has to participate in the M1 interrupt acknowledgement cycle and deliver the 1-byte vector number during that acknowledgement cycle. That vector number is used as it is for the least significant byte of the address that's combined with the I register to find the location in memory that stores the address of the subroutine that's going to be called to handle the interrupt. All right? It's a lot of jumping around. Keep it straight. How big is the table? The table starts at FE00 and goes up to FEFF, okay? Therefore, it has 256 total bytes in it. Each entry in the table consumes 2 bytes. Therefore, there's 128 vectors, maximum, we can say, in this table. All right. Now, vector 0 is the first one. Its address is in the vector table starting at address FE00. Consumes 2 bytes, therefore the address consumes FE00 and FE01, those 2 bytes in memory. The second vector here is not called vector 1, it's called vector 2, because the definition of what you do with this vector number. There is no vector 1. Okay, now in theory, there really could be, because if the peripheral did generate an O1, then it would go into a table that starts at FE01, and it might read this byte here and this one over there, and use those as an address. That's kind of a cockamamie situation that actually we'll see cannot happen with the standard Z80 peripherals, because they're designed to supply vector numbers that never end with an odd value. So, I mean, it's kind of a cockamamie situation, but yeah, in theory, yeah, that could happen, but don't do that, okay? So what happens is these vectors are always going to be even numbers, so they'll start at 0, 2, 4, 8, C, and then move on to 1, 0 in hex on up to FE would be the vector number 127, which is the 128th vector in the list of the all of them, because the first one's number 0. Okay, so every pair of numbers in here represents an address of some subroutine. These subroutines we refer to as interrupt handlers, because they're called through this vector table to handle the receipt of an interrupt signal. Okay, so this is the basic thing we have to create and configure so that we can then tell the Z80 to handle the interrupts, and then it'll use the lookup table here to figure out where to go. So let's look at some code. This is the test code routines to check out the board of the Z80 Retro project on GitHub, right? So this is where I cloned that directory. I showed you this in earlier videos. These are all the files. Let's look at ctc2.asm. What is going on here? What does the doc say? Test program for the CTC and the SIO. I'm going to run channel 3 of the CTC with interrupt requests enabled, and I'm going to use that to implement like an uptime timer. So it's going to be a free running timer. It's going to be a counter that's going to have its value stored in the memory somewhere and just periodically be incremented every time that the CTC channel 3 generates an interrupt. In order to run this demo, I want to have the SIO configured such that J11A is on X2. In other words, SIO is going to run at 115.2. We're not controlling it with the CTC in this example. We're just going to run it at 115.2, okay? Keep it simple. The usual beginning, include the ports, set up the, copy the code out of the flash into the memory, and set up the stack, okay? What do we need to do? We want to run in mode 2. So the first thing we need to do is tell the Z80 to enter interrupt mode number 2. From now on, deal with interrupts in mode 2. Then we have to set the I register to some value that represents the most significant byte of the address where our vector table is. So I'm going to create something called vectab. We'll look at that in a second. And I'm going to fill it up with the pointers and stuff we just talked about. I'm going to get the address vectab. This is a label. I'm going to divide that address by 256, which is a hexadecimal 100. And in doing so, then register A will be loaded with the whatever the most significant byte is of the vector table address. Okay. Now this, of course, is performed by the assembler, and it's not done at runtime. This division is done during the assembling process. The assembler knows where the vector table is, and it knows that if it divides it by 256, what I'm really doing is throwing away the byte on the right half of the address and keeping the left half. That's what gets in A. Okay, I then need to put A into the I register because there's not an instruction that says load the I register with an immediate operand like I do here. All right, so we got to do this double leapfrog thing. This is because, you know, this is only going to be done once, usually when a Z80 boots. Why should they waste all the complexity to support many different modes just to load the I register? Okay, you don't use it like you do all the other ones, A and B and C and so on. All right, so this is a limited type of thing. Anyway, so you get that set appropriately. Let's go ahead and take a look at the vector table while we're sitting here. It's at the very end of the file. It's down here. Vector table. I then have another label right next to it in here that represents the first entry that we're going to use for the CTC. All right. Now this vector table is only going to have 4 vectors in it, one for each of the 4 channels of the CTC. As we're going to see, the CTC doesn't have a single vector that says, hey, the CTC needs attention. Okay? No, it doesn't work that way. It does us a huge favor. It not only has a way of generating interrupts, it has a way to generate an interrupt and give us 4 different vectors. So when the interrupt goes off, we don't only just know it came from, the CTC. We can tell which channel it came from. So we're going to define 4 different handler pointers, vector pointers, in our table here. One for channel 0, one for channel 1, channel 2, and channel 3. And as the doc said above, channel 3 is the one we're really going to use. These are not going to get used in this example program, but we're filling them in anyway. The CTC is all or nothing. It's going to use 4 vector slots. If I enable the CTC to generate interrupts on all 4 channels, it will need to use all 4 of its slots, okay? And we have plenty to waste, so I'll just fill them all in right here, all right? This is the one we're going to use. It'll be the vector number. This is going to be vector 0, 1, 2, and 3 here. Oops, 3 down here, okay? And there's nothing else in here in this example. I mean, we wanted to, we could add vector handlers for the SIO as well, but let's not overcomplicate our first example. Now, in the simplest case, guaranteed to work every single time, let's not complicate this example. If you want to discuss this in the comments below, feel free to do so. If anybody knows a better way to align this table than what I've done up here, feel free to chime in, okay? So this is not optimized to use the least amount of memory. In this particular example, this is optimized to be the most easy to understand example and guaranteed to work all the time, every time, all right? And by that I mean what? If this vector table starting address works the way I just drew it up in the diagram, such that the address that represents this label right here ends with 2 zeros in hex, then everything is real easy. You can do it all in your head, and it's really obvious what's going on. Now, you can play games. You can align this to other addresses. Yeah, I know. But then things get more complicated. And let's not mess up this example, all right? So how do we make sure, then, that this vector table will start at an address that ends with 2 hex digits or zeros? Well, we can use logic like this up here. Now, most modern assemblers have a simple directive that simply says align, and then you tell it, I want to be aligned to a multiple of a hexadecimal 100 in this particular example, which is hex for 256. And the assembler will just do it. Now, the anemic assembler that we're using doesn't seem to have such a directive, so we kind of have to do it another way. And here's how I'm going to do that. This is a directive to the assembler that says if this expression here is a non-zero value, then assemble this code here. Otherwise, don't assemble this code at all. In other words, if I'm already at an address that ends in 2 zeros, and this expression right here will be false, or it will be 0, because $$ is the current address that the assembler is filling data into when it's assembling the code. And if I AND that with a hexadecimal 00FF, then the result of this AND operation will be 0 if and only if the address, which is $, ends with 2 zeros, and these two, right, the least significant byte is all zeros, okay? You can go off and think about that if it's not immediately obvious to you. This operation here is the binary AND operation, okay? Now, if it is not already a multiple of hexadecimal 100, then I'm going to say create a block of storage and pad it I mean, you're just wasting memory. Fill it in for the number of bytes given by this expression right here. And I want 100 in hex, which is 256, minus the value in this expression right here, which would be the number of bytes in hex, the way I've written it here, past the closest multiple of 100 that have already been filled in. Okay, so what I really need to do is calculate how many more bytes there will be between the point where I'm start assembling this statement and where the next multiple of 100 in hex really is. Okay, that's what this expression does here. And this value over here simply says when you're padding all those bytes, you're just filling memory, fill it with this value here. I mentioned this before. The Flash programmer runs faster if you program it with an FF than if you program it with any other value. So when you're padding memory, if you don't care what the value is, sometimes you do. In this case, I don't care at all. When you don't care, set it all to binary ones, which is a hexadecimal FF. Okay? Now the programmer just gets done sooner. Okay, so this fills up memory to make sure that this label here will start in an address that is always going to be a multiple of a hex 100, which is the worst case scenario for requirements of where you want to put your vector table. If this starts at a multiple of a hex 100, then you're guaranteed that this vector here is a multiple of 8, which you'll see if you look through the CTC datasheet, is a requirement of the vector number that you give to the CTC for channel 0. Okay, it must be a multiple of 8, okay, just due to the way that the chip is designed. All right, so if this is a multiple of 100, this is guaranteed to also then be a multiple of 8, and you can do the math in your head when you take the I register, which is the first 2 digits of the address, and then the vector number, which is the second 2 digits of the address, and you can easily look up where they are in the table here, okay? Feel free to run off and complicate this all you want to make optimizations and reduce the amount of wasted memory up here. That's a different discussion, is what I'm saying here, okay? So that's what goes on in this vector table. Okay, so that's what happens up here. What is going on right here? Well, I need to tell the CTC its vector number. Okay, now let's go back down here. Because I just happen to put it at the beginning of the vector table, right? In a general sense, what it really would be, if there are other vectors up here, okay, because maybe some other peripherals are configured, the CTC might have its vectors below and deep into this table is my point. Then what I would know is that the beginning vector number of this first one here would be at the address of this label minus the address of that label. Because there's nothing between these two, it'll turn out to be 0, which is exactly what it should be in this particular example. Okay? But I'm giving you a general purpose sort of thing. Again, it's going to be more flexible if you want to reuse it in other scenarios. Okay? So, when the CTC generates an interrupt request during the acknowledgement cycle, because the vector table is like this, and it starts at an address that's a multiple of a hex 100, the vector number that comes from the CTC will be 0 if it came from channel 0. It'll be 2. Remember, these are all 2-byte values. DW defines 2 bytes. DS defines 1. Okay? So the vector number for channel 0 is 0. The vector number for this is going to be 2. Or more accurately, we might say the interrupt acknowledgement vector value that the CTC has to provide for this channel will be 2. This will be 4. This will be 6. Okay? Because the vector number that comes from the device in mode 2 is added to the value from the I register. When you add the 2 zeros, you append 2 zeros to the value of the I register and then add it to the vector number that came from the peripheral, all right? And each of these are 2 bytes. Okay, so all that in mind. All right, so then what are we doing here? I'm going to load the accumulator with the value that I want the CTC to use for its first of the 4 vectors but it assumes I'm initializing in my vector table. I'm then going to call initialize CTC IRQ. Now, looking ahead here a little bit, right when that comes back, I'm going to initialize CTC port number 3. I'm going to initialize the SIO. We've seen this before. There's nothing new there. Then I'm going to print some stuff out and go on our merry way. All right. So this is really about these two functions at this point, followed by regular old code we've seen before. Okay. So let's look at the CTC code, which comes from this file right here. Okay, so what did we do? We called the init IRQ. Now, the only thing this is going to do is it's going to take the A register, which we've initialized before we called this function, and it's going to store it into the CTC0 control register. Now, we note in a comment over here, the LSB is going to be 0. All right, now, if that's not the case, then this whole thing will break. All right, it will be 0 as long as you create your vector table and you do the initialization the way we just went through it. Okay, with a proper alignment and stuff like that. Okay, for the math that I use to set the value of the A register here. Right. So the only thing we really need to do is simply store it into the CTC configuration register. Now, back in the peripheral user manual here, there's a link to this below in the description of the video. We can see the control register that we're writing to there, all right? Now, we've seen this before. This is where you set whether it's in counter or timer mode and what prescaler do you want to use, that sort of stuff, okay? The bit down here, which we've always set to 1 in the past, we're now going to set it to 0, okay? So this table here represents what all the bits mean. This simply names them up here, all right? Now, if this bit down here is set to 0, then none of these are being altered, okay? When we set the vector number, which is what we're doing, what we're going to do is store the accumulator into the vector number rather than update all these values in here. So there's another diagram down here somewhere that talks about what happens when you load the vector, which is right here. Okay, so when I store a 0 in the control word, I'm writing the vector value. Notice that I can set these bits here, 3, 4, 5, 6, and 7. I cannot alter these 3 bits over here. Now, once again, our favorite art department labels these as both readable and writable. I can assure you these are not writable. This is another crappy drawing. Okay, so how does this then work? Well, bits 3 through 7 are supplied by user. These are the bits that I'm setting when I initialize my CTC for interrupts. Okay, that's what I'm doing. I'm setting this user settable vector bits right here. And this value as a whole is the value that's going to be supplied in the interrupt acknowledgement cycle. So while I can alter these bits, what happens is during the acknowledgement cycle, the CTC will supply what I said here. And for these 2 bits, it'll put a 0 if the interrupt comes from channel 0, and a 1 from channel 1, and so on, in these 2 bits. This bit over here, this is a terrible example, will always be 0 in the interrupt acknowledgement cycle, okay? Therefore, these last 3 bits will always be an even number, and this is why the vector table has to start at an even numbered address. Okay, and these 2 bits always represent the channel numbers. And because channel number 0 has a 0, 0 in here, this one also must be 0. Whenever you have a binary number that ends with 3 zeros, the rest of that number must be a multiple of 8. And that's where the multiple of 8 jazz comes in. If you don't follow this, take out a piece of paper, draw up all the binary bits, work it out, okay? This sort of thing happens all the time when you're working a low-level hardware kind of situation. Why? Because it's cheaper to build the circuits if you make them work this way. Alignment is your friend if your goal is to save money, all right? That's all I'm going to say about that. So this was going on with the vector number, and this is how the vector number is used when an interrupt is generated by the CTC. So all that is why the only thing we really need to do is set this value and store it into the control register. Okay. Now that's the init IRQ function. The other one was like init channel 3. This guy right here. Okay. Now let's look at what's going on here. Thank God I commented this thing. So set the CTC to free run, generating interrupt requests at the system clock frequency divided by 65536. If the system clock equals 10 megahertz, then the rate will be, I said 152 hertz, approximately. 152 hertz. It won't be exactly that, okay? Note that it is okay to enable interrupts before we send the time constant because the yada yada. Okay, this is important because, in other words, I can do all this in one single write operation. And by that I mean I can reset the channel. We talked about this before in the last video on how to use the CTC, the reset, and how to set the time constant and stuff like that. I can set the reset and I can enable interrupts at the same time. That's what this note means, okay? So what am I doing? I have the control bit on, so this binary, or the hexadecimal 7 here, is a 0111. That has a 1 for this control bit in it, right? That's the least significant bit. I'm going to assert that I want the channel reset. I'm going to tell it that I'm going to follow this byte with a timer constant down here. I want to use the 256 prescaler. I'm going to run in timer mode, which means it's going to run using the system clock phi. And I want interrupts enabled. Okay, you can look up all the bits in the manual and figure that out and make sure I did that right if you want. I've tested it, it works. I'm pretty sure it's correct. So we take that value and we write that out into the control register. The next thing we're going to write out, I'm going to put a 0 in here. If you dig through the manual, it specifies that 0, remember we have an 8-bit counter in our CTC. If I set the time constant to 0, I'm going to then be dividing the input frequency by 256. If I divide it by 1, I'm dividing it by 1. If I put it to 2, I'm dividing it by 2, and so on. But 0 is a special case, right? You don't want to divide by 0. That doesn't make sense. So what they did is they made 0 equal, be the same as setting it to 256, which you actually cannot do because you only have 8 bits, and 256 is a 9-bit value. So this gives you one extra value that you can use, a little optimization they did for us, okay? So by setting it the largest possible value is the point, it will go as slow as it possibly can. Now keep in mind, I've got the 256 divisor prescaler on there. So we're going to take the system clock phi, and it's going to be divided by 256 before it's fed into the timer. And with a time count value of 256, it's going to divide it by 256 a second time. Therefore, the math is going to be the total system clock rate, which is phi, divided by 256 for the prescaler, divided by 256 because I said so. Okay? And if phi is 10 megahertz, as I said, it's going to run about 152 hertz. That's the rate at which interrupts will be given to the CPU because I told the channel to generate them here, okay? So I'm going to write my 0 in, and I'm going to return there, okay? So let's go back to the main program and review real quick what's going on there, right? So I did an initialization of the CTC vector number. All I did is store this value into the vector number. I then did this, which put it into free running timer mode, and it's going to count at it's going to generate an interrupt, I should say, at approximately 152 hertz. Okay, I'm going to turn on the SIO. I'm going to enable interrupts. This is the instruction we use to enable interrupts. The Z80 will now recognize them. If you don't do this, the CTC will generate interrupts, but no one's around to hear them. You just muted your phone, right? You can't hear your tweets or whatever you're going to spend your time becoming interrupted by, okay? In other words, we're going to unmask the interrupts, allow them to take place, okay? Then we're going to do the usual stuff that we've been doing before. We're going to print out a blank line. We're going to dump out the memory that represents the code. Then we're going to fall into a loop down here. Now let's have a look-see at what this loop is going to do. Here's the whole thing. We're going to halt the CPU. Then we're going to do some stuff, and then we're going to go back up to this loop here, and we're going to halt it again. Okay? So here's another thing we need to understand here. What does it mean to halt the CPU? Okay? Now, a Z80 never really halts. Right? If you look up what the halt instruction does, the documentation says that it causes the Z80 to continuously execute no op instructions, the do nothing instruction, over and over again. It doesn't actually stop it. Modern CPUs that have halt instructions literally stop. They shut down their clocks, they go into a low power standby state, and do all this other really cool stuff. Z80 doesn't do that. The reason it does not do that is because the Z80 was designed in 1975, 76 release, when dynamic memory was the preferred low-cost option. And dynamic memory back then did not have a mode whereby it could refresh itself. It was too cheap, too anemic, too simple. Something somewhere had to constantly tell the dynamic RAM chips in a system that uses them when it needs to be refreshed. And the Z80 has a special feature during the M1 cycle where it can assert the refresh signal. Therefore, if you actually did stop the Z80, then the refreshing would stop and the memory would all forget their values. All right, so that would be a bit of a problem. So this is actually a feature. While you say halt, what you're really doing is saying, don't go down here until you have processed and returned from an interrupt of some kind. Now, there's one other thing that happens. This, when you do a halt instruction and the CPU stops executing your program, it does stop running code, but it's just spinning and doing nothing, okay? But it's going over and around and around and around. It's just continuously executing M1 cycles, is the point. But it also asserts this signal here called halt. And as you can see in our drawing, here's the CPU, along with the other signals that we're familiar with by now. There's a halt pin right here. When the Z80 executes the halt instruction, this becomes asserted as true, which goes low. So you can use this. You can put an LED on there or whatever. I didn't do anything with it in our design. We just pull it up and ignore it. Actually, it's an output. I didn't even pull it up. This is just not connected in the design. It's labeled and you don't see an X on there because it does get connected to this header over here. So if you want to put a scope probe or something on there, you can look at it and see that the halt does get asserted when you do in fact halt the CPU. Okay? Now that's what this instruction does. Now we don't really care that we've asserted the halt signal at all. Therefore, if we want to, we could just completely comment it out like this. And this code would make no real difference. Okay. One would argue, I would argue, you should halt it anyway. It's just good practice because most of the code you're going to write and get paid for these days are running on modern CPUs. And if you have nothing to do but wait for an interrupt, you really do want to halt. And even more so, way more so if you're running on batteries, okay? You want to get that sucker into low power standby mode if you absolutely, as often as you can. And halt is how you normally do it on a regular modern CPU, okay? So enough said about that. Now, whether you halt or not, what happens is I don't actually want to print out this is going to print a hex dump every on a periodic basis. I don't want to do this 152 times a second, okay? Because I'd have to print really fast for that to happen, and I might not be able to keep up. Okay, so that's what's going on right here. Okay, so what I do is I fetch the current clock value. I guess we should talk about the handlers for a minute here. Spoiler alert. When the interrupt is generated by the CTC, and we go through this table down here, and it calls this interrupt handler for CTC channel number 3, what it's going to do in that code, and we'll look at that in a minute, is it's going to increment this global variable that we've created, and is called uptime. And what this is it's a 4-byte value that represents the total number of times that the interrupt handler has been called since the system is booted, which is roughly what an uptime clock is. This gets updated at 152 point some odd times a second. Now, if I just said halt here, and then I immediately called Hex Dump and went back up to this loop, what would happen is this will wake up 152 times a second, and each time it's going to try and print this Hex Dump out. Now, for fun, we'll put an F0 in here and see if we can even keep up with that. I don't think so. The ability to keep up, by the way, will be dependent on the baud rate. The slower the baud rate, the harder it's going to be to keep up if it takes forever to print something, right? So what I've done is I put some logic in here, and well, this is really simple. What it does is it says, give me the current uptime value. And I don't know why, honestly, I put it in the HL register. This is a little bit convoluted, but you can follow it along. We're loading half, by the way, of the uptime value. As we'll see, this is a 4-byte number. Loading 2 bytes into the HL register. Okay, we're loading the least significant 2 bytes into the HL register. We're then loading A with the L register. So what we're really doing is loading A with the least significant byte of the 4-byte value that is this uptime variable that we're managing in our interrupt handler. Okay? Then we're going to do an AND instruction, and we're going to say if the result is not 0, go back up to this loop. Now, this is the same kind of logic we saw before when we were aligning the vector table. What happens if I AND a number with 3F? If it is equal to 0 after that, it means that all the bits in this hexadecimal value in the register A had to already be 0. Okay? So what are we doing here? We're asking if the accumulator is a multiple of 40 in hex. If you don't believe me, write it out in binary, work it out in your head, convince yourself that it's right, okay? If it is not a multiple of a hexadecimal 40, we go up to this loop and we keep waiting. So this is going to go around here 152 times a second. And once in a while, hexadecimal 40 times per second, which is what, 64 in decimal? 1 every 64 times around this loop, which is a little faster than a half a second, okay? A little less than a half a second in time. It's going to come down here and it's going to do a hex dump. And it's going to do a 4-byte, I should say there, 4-byte hex dump starting at the address that is the 4-byte uptime variable value that's stored in memory. Don't print fancy and just dump it out. And here's another spoiler alert. We'll talk about this in a minute. So just over once every half a second, this loop will come down and hex dump out something that is this uptime value. Now, let's take a look at the handler for CTC3. Now, if nothing was going on in the system, what did I change? Editing, I was playing around with comments. If nothing else is going on in the system, in other words, if there were no interrupts or the interrupts were not enabled, that loop would spin and nothing would ever really happen. But because I said go over and execute this function here, whenever an interrupt comes from CTC channel number 3, it's the init code. Why don't we find the handler code? There we go. Here's the handler code right here. This is what gets called every time there's an interrupt. Okay? And what we're going to do in here, we're going to see what we're really going to do is we're going to go down to this value here and we're going to add 1 to it. Okay? Each time this handler is called. This is a complicated way to add 1. All right? And the reason we have to do it complicated because the Z80 does not have a way to add 1 to a 4-byte value. A 32-bit unsigned value is what we want to use for our uptime. Okay? Otherwise, it'll overflow too often. Right? If you're counting at 152 hertz, and it can only go up to 65536, which is what you get for a 2-byte value. Remember, we're defining words and initializing them to 0 here. So there's a 16-bit value there and a 16-bit value there. Combined, it's a 32-bit value. Okay, so the uptime variable in the storage down here, if you're writing a C program, think of it as a uint32 type variable. Okay. Now, what's going on up here? When you get an interrupt, think about that. Remember, what we're doing is we're interrupting any code that might be running when the interrupt arrives. In this particular example, our intent is for it to interrupt the halt instruction. Arguably, it's not doing anything of value. However, it could be doing something of value. So we need to save all the registers that we might modify in our interrupt handler so that we can then restore them again before we go back and resume the program that we've interrupted. If we don't do that, and all the registers just randomly change their value, anytime an interrupt comes along, you'd have a really difficult time writing any code, all right? That just doesn't make any sense. So we want somehow or another, and this is the simplest way, there's more optimal ways to do these things. This is written to be understood, not to be perfect and the most esoteric and beautiful thing ever. We just need to save the registers that we're going to modify. We're going to modify the HL register because we're using it right there. We're going to add 1 to it, and we're going to store it back in there. We're modifying the A register, so we have to save that as well. And we're also modifying the flags because we're going to do an OR instruction down here, which modifies the flags, okay? So what does it mean to add 1, then, to a 32-bit value when you don't have an instruction to do it? Okay, so let's look closely. Load HL with the value in memory stored at the address represented by this label. Okay, so it's going to load HL with this value here. Going to add 1 to it, and then it's going to store the HL value back into there. That's great. Kind of seems confusing. But remember, this is a little endian machine, and the 4-byte value here is going to be in little endian order, which means if you lay this out 1 byte at a time, I could go down here just as easily and said define byte and put 4 of them. That might help a little bit. This first byte here, at the lowest of the 4 addresses of these 4 bytes, is the least significant byte. It's backwards in little endian. The most significant byte is over here, okay? As humans, we normally count, and if I told you a number was 105, those digits are given to you in order from the most significant to the least significant, okay? But in Hex, the byte ordering can be reversed, and that's what little endian is. Go ahead and Google it and read the Wikipedia page on it. I think earlier in the sequence of videos, I showed you a document I give to my students. It's a work in progress. Please excuse the notes to myself in there, called RISC-V Assembly Language Programming, where there's some tables and stuff, and I talk about byte ordering, big endian, little endian, and stuff like that. So if this is the first time you've ever heard of it, you can go in there and look at that if you want. I'll put a link to it below the video in the description, okay? Anyway, this is in little endian order, which means that if I want to add 1, I need to add it to the least significant byte, and then if there's a carry, it goes in this direction in terms of increasing address, right? So what do? I grab the least significant 16 bits and I add 1 to it, put it back in there. Then I grab the value of the H register and I OR it with the value of the L register, and then I ask, is the result of that not equal to 0? If that's true, I go down here, which goes to this label there, and I leave. So what's this thing doing? I'm asking if HL, after I added 1 to it, is a value that is not equal to 0. That's how you do this. Because if it's not equal to 0, I know that I did not do this addition here and end up with a carry. Because if HL, when I loaded it from uptime, was FFFF in Hex, and I add 1 to it, it would have become a 0. And there would have been a carry that would have been thrown away. in this operation here. So by asking if HL is 0 after this addition up here, I'm asking, should somebody go over here and take care of the carry and add that carry to the other half of this 32-bit value? If the answer is yes, I come down here and I go grab the value at uptime plus 2, which is this 16-bit value, these 2 bytes over here. I then add 1 there to deal with the carry and store that thing back, fall down here, restore the registers, and then I go back to where I came from. And before I do that, I need to re-enable the interrupts. The Z80, when it gets an interrupt request, the way it handles it is it shuts off interrupts, it masks them, so that it can't get nested. It won't be able to, you can, if you want to, enable nested interrupts on the Z80, but by default it shuts them off so that when I'm handling an interrupt here, another interrupt can't interrupt this interrupt, okay? It's very important you have to write your programs very carefully if an interrupt handler can be interrupted itself, especially if it's recursive. In theory, this could actually interrupt itself if you got really creative with your hardware, okay? The Z80 does you a nice favor. By default, it doesn't do crazy stuff like that. It's all up to you to create your own levels of crazy. So when we enter in here, interrupts are disabled. I have to re-enable them when I'm done, is my point. Well, then, in order to go back to where I came from, I don't simply return like I do in a regular subroutine. I have to tell the Z80 that I'm returning from an interrupt. And the reason I need to do that is because the fancy mode 2 peripherals actually continuously snoop the data bus and watch what the CPU is doing. And it looks to see if a return from interrupt instruction is being executed. And the reason it does this is so that if multiple things are interrupting at the same time, it can figure out that one of them's done and it's time to then assert a different interrupt and let that one take place and so on. All right. I'm going to leave it as a test to the reader to deal with understanding what return from interrupt does and return from non-maskable interrupt really does. Once you get interrupts understood, you can read the manual and you can understand that stuff. The good news is it just does the right thing that's supposed to happen if you've got a Z80 and you've connected it to the Z80 peripherals in the prescribed manner, which is what I've done on the Retro board. So if I don't want to allow interrupts to become interrupted, which is by default how it works, I just write an interrupt handler like this. When I'm done, I re-enable the interrupts and I say return from interrupt. And all will be fine. You can take this as this is how you write an interrupt handler. Okay. Okay, so let's go back to our main program here. So what does that mean then in here? This now makes sense, right? So every time the halt instruction returns, an interrupt handler will have completed its execution. And the return from interrupt instruction will come back to and complete the execution of the halt operation. So the return interrupt will start causing the Z80 to resume and fall down and execute this code. And that's why if we go over here at that time and grab the uptime variable value and look at the least significant byte and ask if it's a multiple of hex 40, and then and only then print out a hex dump, then we'll be able to see a little hex dump coming out. Just a little bit more than twice a second. So let's grab our favorite terminal here and make sure that all of our programs are compiled. Well, let's get the terminal out of the way for a minute. We got to program the firmware. We do that. Look at the README file. We've seen this many times. So we're going to run the Flash programmer, and we're going to program. We did just ctc2.binary. Now I'm going to put this in here because we're going to watch it go. Remember, the Flash programmer will download the code into the ROM and then reset the Z80, and it'll begin running right away. So what happened in here? Couple of things. We just saw a hex dump spew out. We see all these FFs in here. That's the padding. This right there. Let me see if I can stop this. Okay. By the way, if you're in Minicom and you hit Control A, Okay, what that is you're entering this help menu. I did not yet hit the Z, so if you hit Control A, Minicom will stop and freeze, and then you can just use your regular mouse and scroll up and down and see what's in the terminal. And it's just buffering all the other data up that will come out later if you hit escape or something like that, and it'll resume printing. So here's the hex dump of the program. You can see, we can look at the listing file, and we can see that this is all going to jive. Our code ended here, and this is the logic where I said, well, just fill up all the data with FFs until you have aligned the next instruction or the next data address to start at a multiple of a hex 100, and 200 is an obvious multiple. And in there is our 1, 2, 3, and 4 pointers. This is our vector table right here, okay? Down here, once this thing boots up, is it printing out its uptime? Remember, it only is going to print the hex dump when the value is a multiple of hex 40. And because it's little endian, this is the least significant byte. So you might say the value of the uptime counter at this time when it printed it out here is 00000040. And it goes to 000080, 0000C0. These are all multiples of 4. Once we get up from C0 and we interrupted it 64 more times, we see a carry in there. So this is 00000100. Okay, and so on. It'll keep on going. I'll hit the space bar, and you'll see the Minicom resume, and it'll just do this. Okay, so this is proof that we've got interrupts being handled, the uptime counter is advancing, and it's kind of mysteriously happening, and the program that we wrote isn't the thing that's doing it in the main loop. And by that I mean our spin loop is not advancing the counter, it's just happening while the spin loop runs. And the reason it does this is because interrupt the handler is doing it, right? So when this thing runs, and we see it become a multiple of 40, we dump it out, okay? So let's go ahead and comment out the halt. I don't think this is going to make any difference in our program that we're running here. Let's bring our terminal back in. We're going to repeat the flash programmer command, and if you know how to use history in the shell, bang means rerun the last time I typed in a command that started with a tilde. I'm not going to type the whole thing in again, it'll just simply do it again. Now, what's going on here? Wow, this is amazing. Oh, this is funny. So this is not the same thing. This is a great example. What's happening is, look, every time it prints out something, I don't know, like 4 times. So we got 80, 80, 80, 80, right? Then we got the 81 here, and then we got this. It's kind of going nuts and coming out all over the place. Why do you suppose that's happening? Well, it's happening because when the loop runs, it sees an 80 in the variable. When it does this logic right here, this actually is a perfect lead into the next example program. When it does this, it reads the value of uptime. And it asks, is it a multiple of 40 in hex? Yes, it is. So it goes down here to print it out in a hex dump. Time passes between the point in time when it fetched it here and it asks, is it a multiple of 40? And the time it gets down here and starts printing out the hex dump. By the time it gets down here, the timer could have advanced. So that's one of the things that this comment is referring to here, okay? It turns out that the counter advanced between here and here in the scenario we're looking at right now. Okay? Now it can also advance while we're in the hex dump routine itself. And that can do all kinds of crazy things. By putting the halt in here, what happens is this accidentally creates a situation where we don't have these kind of weirdy, wonky timing problems. Because I have to get an interrupt in order to ask this question. And if I've done a hex dump and I printed out a value, and I go up here and I wait for the next interrupt, if I print out the hex dump and I come around here and I don't halt, and I immediately check again, if uptime has the same value, that it had last time I went around this loop, it's going to try and print it again. Okay? So if uptime is hexadecimal 80, right, or it ends with a multiple of 40, more accurately, like, for example, the 80 example that we saw, okay? And it's still set to that value. When it fetches it and looks at it a second time, it's going to try and print it again. Maybe it'll come back up here. If it doesn't halt, it'll ask again. What's the value? It might still be 80, okay? So it prints it again. So it's going round and round and round and round. The number of times it'll print it will be dependent on the bit rate, right? The slower I print, the less likely it's going to be able to print it and go around and see that nothing has changed yet and do it again and again and again. Okay, the last time it goes through there and we see is this random junk value that's not a multiple of 40 is because we fetched it and it was a multiple of 40 and then it changed, like I said a minute ago, and then I try to dump it again, and when I'm dumping it, remember, I'm not dumping HL, I'm dumping the value that's in memory. And because that value in memory could have changed if an interrupt took place here or an interrupt took place here and so on, I can end up printing out something that doesn't really make a lot of sense. Okay? Now, you might say putting halt in here fixes it. No, it doesn't fix it. This is really a dangerous and lame thing to do. This is a really bad situation. This is an example of a program for the sole purpose of showing you that interrupt handlers work, but this is in no way, with or without this halt, in no way an example of how to use interrupts to print out the uptime. Okay? Now let's move on to resolving that problem. Okay? Interrupts work. We know how to do them. Part A of this video is done. Let's go ahead and move on to Part B, which unfortunately is the file named CTC2A. Okay? All right, so this version of the code is identical to the last one, except I've done some minor changes. For one thing, I've changed the SIO configuration so that I can change the baud rate, so that I can really emphasize what happens if we waste a lot of time printing. That's really what's going on here, all right? Same startup, same vector table, same CTC3, 152 interrupts a second. This up here, I simply configure the CTC so that I can generate a really slow bit rate. And in order to go nice and slow, we're going to change the SIO divider to be 64 instead of 16. We've never done that before. But what we're going to do is just reach down in here after we've initialized the SIO in the usual way. We're going to just replace the value that we put in register 4 and change this bit right here, these 2 bits, and tell it to run in divide by 64 mode. Okay? Until now, we've run it in divide by 16 mode. And once we're there, we're going to print our blank line. We're going to do the usual dump here, and then we're going to fall into the loop. This is the same code we were just looking at before. But if we run it really slow, even with the halt, we're going to see craziness because, for the same reason we just saw craziness a minute ago, it's going to go through here, it's going to wake up, it's going to say, oh, it's a multiple of hex 40. It's going to start printing it, and it's going to take so long to print it, the interrupt handler could fire several times before it gets done with this thing. And it's going to go back up to the loop and go over and over and over and over again. All right. So that's the only difference. Now, to make this program work, up here, hopefully I have it in the notes, I need to jumper the X2 jumper on J11A. This, I'm going to move it over to the CTC because I'm going to run the SIO much slower than we are in the CTC2 example we just looked at. All right. The only difference is I'm going to generate a bitrate clock and run it at 300 baud instead of 115.2. Big slowdown. Okay, so I shut off the Pi. I rejumpered the retro and powered it back up. Here's the minicom. I'm running at 300 baud, 8 on 1, and let's make sure all the code's compiled up. Let's reprogram the flash for CTC2A.bin and watch it go. And you really want to know what the retro vibe really is. That's 300 baud, okay? If you had a dial-up modem in 1980, this is what you dealt with. This, of course, you were made of money, and you had one of those newfangled 1200 baud modems that were, lightning fast in contrast to this. This was what BBSs were like for those of us kids that could even afford to make lousy phone calls back when everybody had to pay by the minute. God forbid if it was long distance. We all had phone bills that were stratospheric. Thank you for the internet. No matter how much you pay for the internet, it's less than one of my monthly phone bills back in the day. Or at least a couple of them were up there. Anyway, this is 300 baud. We probably should have commented out the dump part of the program, because this is just an eternity. Be that as it may, the point of the whole thing is to run this slow enough that we're getting multiple interrupts while the thing is printing and it can't even keep up. Look at these values in here. Okay, it's certainly not multiples of 40 in hex over here, right? What are the values? We got 54 and D3 coming out of here. These values, if I pause it, look at this thing. 53, 43, blah, 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 blah. And then it goes to D4, and then it goes 54, D3, 54, D4, 53. All right, so it's like D3 or D4 and a 53 or a 54. What we're looking at here is it takes so long to print this that when the counter advances, there are several interrupts that pass by between the time the logic asks is it a multiple of hex 40 and the time it starts printing. It's already moved all the way up to 54. That's because of how long it takes to print this, okay? So it's probably 4240, and it says, oh, I better print it out. And then it calls Hex Dump, and it reads one byte at a time, and it starts printing out. The 40 has already grown to be a 54 by then. And this may or may not even be the right value that should be here. This could have advanced as well. It could have advanced way beyond what it should be, okay? My point is, because each one of these bytes could advance, they're fetched one at a time during Hex Dump. It might be that by the time it prints the 54 and it goes back to get this other byte here, the 54 could have gone with another value. Okay, this is so crazy slow that all kinds of crazy anomalies can happen. All right, this is what you get into when you're dealing with interrupt handling if you're not thinking about timing in what we call critical regions of code. So I'm way over time in this video. This is actually a two-parter and one big wide. But let's go ahead and banter on a little bit and look and see what we can do about this, because if it really is taking this long, even if it runs at 115.2, this could happen from time to time just because you may not be halting or you're doing something else that consumes a little bit of time before you get back to waiting again, right? So as I said before, the idea that you'd put a halt in there and somehow that would fix your code is foolishness. People that do things like that, don't ask me for a job. I don't want to work with you. Anyway, so the point of this is that this is example code that simply shows that interrupts are happening and the uptime counter is advancing. Let's look at an alternate. So we got if 0, let's throw away the naive version and then look at this version down here. Else, here's another loop that I called safe loop. This is safer, we should say, okay? Now, notice down here I have a safe uptime variable in addition to the regular uptime variable. Then we're going to use that one up here in the logic. So let's see what's got going on up here. So what does this thing do? The comments are, we got an alternate halt loop that's better than the above one, not still as good as it could be, right? In an optimal solution, there would be some sort of semaphores going on between the interrupt request handler and this logic here, okay? Simply using a halt here, like I said before, is not a really good way to synchronize this logic with an interrupt handler. In fact, it's a crappy way to do it. Only a fool would do this in a production piece of code. I only do it in order to demonstrate these instructions and show what happens when they're going on and not going on, okay? Let's first start with the code being the same as it is above, in that it halts, gets an interrupt, it asks, is it a multiple of a hex 40? If it is, what makes this safe? Well, if we grab a copy of the uptime counter here, and then we hex dump it, we hex dump the copy, not the original. Okay? We can disable interrupts while we grab the copy. This tells it, I don't care if you're interrupting, do not interrupt this critical sequence of instructions here, because I want to make sure that I get all 4 bytes copied from the variable the interrupt handler increments from time to time. I want to take all 4 of those and get them copied over to here. And I want to know for a fact that during the time I'm copying it, because I got to read and then write, 2 bytes at a time here. During the time I do this, I shut off interrupts. Disable interrupts. Enable interrupts. This will allow me to get a clean copy of the counter and know that while the hex dump is going, even if it's going super slow, that the first byte goes with the second byte, and that one goes to the third, and so on. All right, so they can't get messed up while it goes. Now, I said this is better, but it's not great. Why is it not great? Well, it's not great because technically, I should also include this comparison up here in the critical region of code where I have the interrupts disabled. Okay, now, how would you do that? Okay. And why would you do that? Well, obviously, if I want to ask, is it a multiple of 40? I want to then move on to say, good, get the copy of that value before the interrupt handler can, change it again. And then re-enable interrupts. So you basically want all this to occur. You call that the critical region of code. Okay, at a minimum, I want to be able to print the time in a consistent manner to make sure all 4 bytes go together. This is minimally tolerable. Okay, however, you may not see a multiple of 40 because the time you check it is up here before you use it down here. If an interrupt should occur anywhere in this amount while any of these instructions are executing, you can end up with a number here that you've copied that's not a multiple of 40, because it could have changed. Could have changed because you have interrupts are not masked off during this time. So let's actually fix it the right way. I probably should have done this beginning. What you need to do is disable interrupts up here and say, look, the critical region starts here. Check it. Is it what I want? If it is, fall through, make the full copy, re-enable interrupts down here, and go on our merry way. In this version of the code, this load here is not needed anymore because it is redundant with the one up here. All right. I mean, there's some optimizations maybe we could do here. Now we have to worry about the fact that if it is not a multiple of 40 in hex, we need to go up here to safe loop. Well, if we halt with interrupts disabled, they can never occur. This is a one-way trip to no, okay? If you ever say disable interrupts, do a bunch of code here and jump up to safe loop, and then you say halt, you're done, okay? This will never do any more work. That's not even a blue screen on a Windows box. That is a complete seizure. So let's enable the interrupts before we halt, okay? We go ahead and put that in the loops here. So what happens here? Regardless of why we got to safe loop, we can enable them. Even if they're already enabled, it's okay to enable them again. It's not a problem. It will halt. We know they're enabled, so this will eventually wake up if we get an interrupt request. As soon as we get one, we disable interrupts. We check to see if it's one that we want to print. If it's not, we re-enable them, halt. That works. That makes sense. If it is something that we want to process, we will fall down here and finish copying the uptime counter value to our local copy down here. We re-enable interrupts here because we want to make sure the counter still runs and that it advances the uptime counter while we're taking an eternity to print it out over here, okay? Before we go back up to the safe loop, no interrupts are already on, so this is redundant, but who cares? It'll then go and do another halt, and it'll go round and round and round, okay? So this will, hopefully, print values that are only a multiple of hex 40, and it'll do it correctly because we've disabled interrupts during this region of code here. and make sure that nothing can interfere with these variables that are stored in memory during our interacting with them and reading them and altering them. Okay? Let's run this one and see what happens. Okay? Bring our terminal back in. It's still running the relatively crappy one. And you can also see we've incremented the high order bit here. When this thing rolled over, it must have gone to something or other FF, and then went and tested that other logic in the interrupt handler that dealt with that high order carry when we added the 1 to the 16-bit least significant word there, just FYI. So let's see what this one's going to do. You know what? We don't have time for this. Let's go through here. That's why I put this marker in here. Let's go ahead and not dump out the code each time. Okay. This reminds me of 1980 all over again. You would optimize all your code to minimize the amount of crud you print when you're running a 300 baud. So you can see this now as all printing out the right values, or at least some of the right values. All right. Clearly, it's not working as well as it did when it was running at 115.2, because you saw 00 something or other, 40 something, 80 something, CO something. You saw all of them. But this one takes so long to print, is my point, that by the time it actually prints one of these lines, the counter is raised by over 64 interrupts, which means this is taking just a little bit more than maybe a half a second to print one line, right? Because this is, the counter's running 64 out of 152 is a little bit more than 2 hertz, maybe 2.5 hertz, and it's counting along, and we're wasting too much time, and we're missing interrupts here, okay? Now, going over all the weird nuances of interrupt handling and locking and critical regions was really not the point of this video here. I just throw this in so that if you decide to tinker around with this code, you start to understand why I got some of the weirdness in there and what it means if you've never done any interrupt handling before. Now, this should be some foreshadowing, by the way. If you're going to write your own BIOS and you got interrupt handlers going on and all sorts of other things going on in your code, you need to be very careful about what you're doing in there, or you could corrupt all kinds of variables and get some really weird results, okay? So when we deal with interrupts, we need to be very careful, all right? So, till next time, thanks for watching. See you on the internet.